Next, we will discuss something called the preparation methods. In the density operators. Let us recall that the density operator rho, any density operator, can be written as sum over I, pi, psi I, outer product psi I. This is the most general representation of a density operator. But if you recall how we arrived at this conclusion was that we have an ensemble of atoms, photons, or whatever is our quantum system, and a few of them are in state psi 1, other are in state psi 2, and psi 3, and psi 4, and so on. And their corresponding weight is probabilities are given by P1, P2, P3, P4. When we since all the quantum systems are indistinguishable from each other, so we cannot a priori tell us, we cannot say which quantum system is in state psi 1 and which one is in state psi 2, and so on. The measurement outcomes will give us an average answer. We will get an expectation value of observable, and it turned out that this density operator is one of a better ways of representing the state, which will yield all the experimental results, namely the expectation values. And from here we saw that the expectation value of an observable is nothing but sum over I, pi, and expectation value of A in the individual state psi I, which can be written in a very short form as 8 times rho and trace of that. Okay. Now we can see that in this way of representing a density matrix, it seems like there are quantum systems, like for example photons. Some of them are in state psi 1 and others are in psi 2 and psi 3 with probability P1, P2, P3. And for psi 1, we have expectation value of A. For psi 2, we have another expectation value, and we take the weighted sum of that expectation values with the probabilities given by the preparation method. So in that way, this representation for a density operator can be thought of as a preparation procedure or method for a quantum ensemble of a quantum system. So this is a preparation method for a density matrix rho, or a quantum ensemble, state of a quantum ensemble given by rho. Now the question is this preparation method unique to achieve rho? It means that if I have two representations, one is sum over I, pi, psi I, and another rho prime sum over j, qj, phi j, will they always be different states rho and rho prime? Is it possible to choose pi, psi I, qj, phi j such that rho equals rho prime? Okay, so can we prepare the state of a quantum system in more than one ways is the question we are asking. So that is what I like to call non-uniqueness, non-decomposition of density operators. Or non-unique ways of preparing state. To understand it, or to get a feeling why we want to find out whether there is a unique method of preparing a state or a non-unique method, let us take one simple example: half times identity. It's a 2 by 2 identity, so this is a density matrix for a qubit. Here the r vector is 0, like 0 vector. All the rx, ry, rz all are 0. It's a valid density matrix because it's a Hermitian identity matrix, Hermitian. trace is 1 and eigenvalues are half and half, both are positive, so rho is positive operator. So it satisfies all the three criteria for a matrix to be called a density matrix. So in that way, this is a valid density matrix. Now we can write half times identity as half times 0 0 plus 1 1, because 0 and 1 are the complete bases, so 0 0 out of plus 1 1 is identity. Similarly, we can write it as half times plus 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 minus minus, since plus and minus are also complete bases, so we can write it as the summation of the mixture of plus and minus. So you see there are two decompositions for the same density matrix. Okay, so probably we can represent one density matrix in more than one ways. So this was just the intuition, and it's very simple example we have taken. We can have a very formal proof also. Okay, so the proof of the statement of the non-unique decomposition of rho. Let us say we have rho, which is of course given by pi, psi I, psi I. Okay, so pi's are the probabilities, and psi I, psi j need not be 0, delta ij. But psi i's are normalized. Normalization is important, orthogonality is not required. Now let us say rho is actually written as psi I tilde, psi I tilde, where we have defined psi I tilde to be root of pi psi I. So psi I tilde are neither normalized nor orthogonal. Okay, we have done it to make it look pretty, that's all. Now let us define phi j tilde such that it's sum over I r ij psi I tilde. Okay, so we are not putting any condition on phi j tilde whether they are orthogonal or normalized. They can also be neither normalized nor orthogonal. They are just some vectors we have defined as a superposition of psi I tildes. Okay, now phi j tilde out of product phi j tilde can be written as I comma k r I j r star kj psi tilde I out of product psi tilde k. We are just using this expression and plugging it in this. Sum over j, if we do, we get ijk summation. Now r star kj, if you refer back to our other lectures, we have r star kj, we can write it as r dagger jk. So we have r dagger matrix and jkth element will be r star kj. We can substitute it here, we get sum over j, phi j tilde, phi j tilde, sum over I, j and k and r ij, r dagger, jk, psi tilde I, psi tilde k. Now if we have two matrices, let us say A and B, and we take the product of them and we want ikth element of them, we get sum over sum over j, A ij, B jk, that will give us the ikth element of the product. We can use this thing, we can say sum over j, phi j tilde equals sum over I k r ij, sum over j r ij R dagger JK psi tilde I psi tilde K. So this thing we can write as R dagger IK. That will be sum over IK R dagger IK psi tilde I psi tilde K. Now, if R dagger is identity, okay, then R dagger IK will be delta IK. This implies that sum over J phi j tilde will be sum over IK delta IK psi I tilde psi K tilde, which will be sum over I psi I tilde psi K tilde. So if R dagger is identity, we have sum over J phi j tilde is row, because this is row. What we have done here is we started with one preparation method of row where we had pi as the probability and psi I as the states, pure states. And then we got a combination or superposition of psi's, and we got phi's, and we found that that also is a valid decomposition of row, valid preparation method of row, as long as phi's is related to psi by matrix Rij. And the condition over R is R times R dagger is identity. First of all, we should realize it's R times R equals identity. This does not mean unitary. In fact, this is identity only from one side, so it's called isometric matrices, not unitary. If it is R dagger equals identity and R dagger R equals identity, then it's unitary. It's only one condition is satisfied, then it's unitary, isometric. So with this kind of condition, we can transform the state psi into phi, and we still have the same density matrix. So our new preparation method is sum over J phi j tilde, and we did not assume they are normalized, but we can say they are normalized now by Qj phi j, where now phi j's are normalized and Qj is nothing but the norm of phi j tilde. So we have pi psi I, one preparation method, and we have Qj phi j, another preparation method. Okay, and these two are related by a transformation R, matrix R, and R is the isometric matrix. And how many isometric matrices are there? Infinitely many. So we have infinitely many ways of preparing a same quantum ensemble row. So what is the consequence of this statement, that there are infinitely many ways of preparing a quantum ensemble? The consequence is the following. We prepare, or an experimentalist prepares a quantum ensemble in a state which is given by pi's and psi's. When we perform measurement and we calculate the expectation values and we reconstruct the state, we get a density matrix. So we start with pi, psi, and after measurement we reconstruct the state, we get rho. We don't get pi psi, we get rho. And this rho can mean it is Qj, phi j, it is Rj, eta j, it can be many other methods. So we don't know which method was used to prepare the state. Once we prepare it and we forget about it, then we do not know what method was used to prepare, and there is no way allowed in quantum mechanics which allows you to reconstruct the preparation method. Okay, or we can say there is no way of retrieving the information about the basis used to create the state rho in a physical setting. If one can find any such method which can find out from experimentally what basis, what psi is and what pi is were used to create the state rho, then that can be used for superluminal communication. It can violate many of the concepts of physics, principles in physics, and that will be one of the topic we will discuss in this course later on when we have learned about the generalized measurements and POBMs. So this has very profound consequences, so which we will not discuss right now. So let us say the state rho is that is given to us is p times 0 0 plus 1 minus p times plus. Let me remind you, 0 is the eigenstate of sigma z and plus is the eigenstate of sigma x with plus 1 eigenvalue. Now, this is one preparation method given to us. Now, our task is to find another preparation method with 3 pure states. Okay, so it means we are given psi 1, which is 0, psi 2, which is plus, with corresponding p1, which is p, and p2, which is 1 minus p. Our task is to find phi 1, phi 2, phi 3 in such a way that phi j is sum over I r ij psi I. From here you can see that R has to be 2 by 3 matrix. So R dagger will be a 3 by 2 matrix. So R dagger is the identity which is 2 by 2. Okay, so R will have the shape which is in this fashion, 2 by 3 matrix, and R dagger will have this shape. So if we write, if we say R dagger is u1 and u2, two vectors, where u1 and u2 are the three-dimensional vectors, then R dagger or R becomes u1 and u2, and condition is R dagger equals identity, which will be u1 u2 u1 u2, which will be u1 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 u2 u2 u1 and u2 u2, which has to be equal to identity. It says that this implies that u1 and u2 are normalized vectors and they are orthogonal to each other. So we need to find two vectors, three-dimensional vectors, which are orthogonal and normalized. So there are many choices of it. For example, we can choose u1 to be 1 0 0 and u2 to be 0 and cos theta over 2 sin theta over 2 exponential of I phi. We can choose this kind of vectors, right? So there are many choices. Let us say one choice we are making, u1 to be 1 1 1 1 over root 2 and u2 to be 1 omega omega square 1 over not 2 3, it should be 1 over root 3, where omega is nothing but the cube root of identity. So our R matrix will look like 1 over root 3, 1, 1, 1, 1 omega square omega, right? So now phi 1 will be R 1 1 psi 1 plus R 1 2 1 psi 2, which will be psi 1 plus psi 2 over root 3. Phi 2 will be R 2 1 psi 1 R 1 2 psi 1 plus R 2 2 psi 2. That will be psi 1 plus omega psi 3 over root 3, and phi 3 is R 1 3 psi 1 plus R 2 3 psi 1, which will be psi 1 that square here plus omega psi 3 psi 2 over root 3. So in that way we got the three phi's, phi 1, phi 2, phi 3. You can check they are not normalized. So let me call them tilde. They are not normalized. Wait a sec. We have made a small mistake. This equation was for tildes, and tildes were for the multiplications of probabilities also. So tilde. Where psi I tilde root pi psi I. So we have to substitute that. And with this, we have found a set of vectors, new vectors phi i's, which there are three vectors now, and with their corresponding probabilities, that will be the norm of phi I tildes. And we can check that the row can be written as phi j tilde, phi j tilde. This shows that a given density matrix can be represented in more than one ways. There is one exception to this rule, and that is for the pure states. If rho is psi psi, then we cannot find any other representation for this state. It has to be just psi psi. We cannot find any other preparation method to prepare this state. It will be just this psi psi. But if there is any small amount of mixedness in the row, any small amount of impurity, then this breaks down and we can find infinitely many ways of preparing the state row. So till now we just saw that we can represent the density matrix in a mixture of 2, mixture of 3. We can have a mixture of infinitely many pure states also. Okay, that will be clear when we talk about the geometric representation of states. So we can represent the density matrix as a mixture of infinitely many states. That's the upper bound, which is infinity. What is the lower bound? How many pure states are required? Minimum pure states are required to represent a density matrix rho. So the minimum pure states required to decompose rho can be achieved from the spectral decomposition. Since rho is a Hermitian operator, so we can write rho as eigenvalues lambda I times the eigenvectors projected over eigenvectors. So this is a spectral decomposition, and the set I is the orthonormal basis. Lambda is the eigenvalues which are positive and real. Positive because it's a density operator. This decomposition will give us the minimum number of pure states required to decompose the density matrix rho. We cannot go below this thing. So this is the lower bound. That will be the equivalent. That will be equal to the rank of rho. For pure state, rank is 1. For mixed state, rank is more than 1. For density for qubits, the maximum rank is 2. So for qubits, we need for a mixed density matrix, we need at least 2 pure states to represent the density matrix, and we can use as many pure states as we want to represent the density matrix. There is no upper bound.